Hello everyone, and welcome to today's webinar from AISC. This is Seismic Load Path for Steel Buildings, presented today by Raphael Sabelli. My name is Brent Liu. I am with AISC's Continuing Education Group, and I want to thank everyone for being here, and I will be moderating today's presentation. I want to introduce today's speaker. As I mentioned before, today's presenter is Raphael Sabelli. Raphael is the Principal and the Director of Seismic Design at Walter P. Moore. Raphael has earned a Special Achievement Award from AISC, as well as the AISC T.R. Higgins Lectureship Award. He is very active in the development of seismic design standards for steel systems, and is a member of the AISC Seismic Provisions Committee, ASCE 7 Seismic Task Committee, and the NIST Building Seismic Safety Council's Provisions Update Committee. Raphael is also the chair of the AISC Seismic Design Manual and served as a project manager for the 5-volume SEOC Seismic Design Manual. He just recently completed writing and presenting AISC's Night School presentation on fundamentals of earthquake engineering, and we're very pleased to have him presenting today's webinar. With that, I want to welcome you, Mr. Sabelli. I'm going to hand things over to you.
Thank you, Brent, and welcome everyone. As you just heard, today we're talking about seismic load path, especially for steel buildings. We've got an hour and a half, and it's a pretty big topic. We'll talk first about seismic design, introducing some of the concepts of seismic design that we'll have to bear in mind as we work through the load path. Then we'll talk about load path in general and what makes the seismic load path just a little bit different from other load path issues. We'll deal with foundations. We'll talk about diaphragms, collectors. In other words, all these things that are part of the load path but are outside of the special moment frame or special concentrically braced frame or eccentrically braced frame or whatever seismic system you have, but still are necessary as part of the load path. And finally, we'll get to the issue of deformation compatibility, which is not per se part of the load path, but is very important for a total seismic design of a building. So, beginning with seismic design, we have a reduced response that we're designing for. So our forces that we're designing for are reduced, and we have to bear in mind why that is and what the effects are. We'll talk about the different force levels that we consider for different elements in the load path, with specific attention to a concept that we often refer to as the fuse concept in seismic design. So you can construct the response of a single degree of freedom oscillator of a given period and get the acceleration due to an earthquake. And you get something that's called a response spectrum. So on the vertical axis, we have the acceleration that a single degree of freedom structure might see, and on the right, on the horizontal axis, we have the period. So the response of a structure is going to be a function of its period, with longer period structures seeing less acceleration. This response spectrum that is drawn here is the elastic response spectrum for what we call the maximum considered earthquake, or MCE. So this is essentially the type of seismic ground motion that we are considering when we design our new buildings. But we don't actually design for these force levels. If you go to ASCE 7 and follow the process step by step, one of the first steps that we take is to take that force level corresponding to the maximum considered earthquake and multiply it by 2/3. To something that a lot of people insist on calling the design basis earthquake, which I guess is as good a name as any, except we're not actually designing at that level. So that's just an in-between step. So after multiplying by 2/3, we do some other manipulations, And we divide by the R factor of the system. And then we get down to a level that we're actually designing for. So this is the force level that we're designing for. It's a couple of big steps down from the maximum considered earthquake, but this is the required strength of the structure. So looking at it for a particular building, you have this building has a certain elastic period. If the building remained completely elastic, it would see forces way up at this level here. That would be the required strength of a fully elastic structure, a structure that remains elastic in the maximum considered earthquake. It would be a very expensive structure, very, very strong, very, very expensive, and so we don't take that approach. If we were designing for it to remain elastic in this so-called design basis earthquake, we'd get some reduction, but still it would be very, very strong. For typical structures, we are designing way down at this reduced spectrum, and the use of that reduced spectrum implies that we will have inelastic behavior. So, designing with an R factor here and with the 2/3 factor on top of it, we are accepting the fact that we are going to go beyond the elastic limit of this structure, and we are going to get yielding. So what we're designing for is this MCE ground motion. We want survival in that event, but our actual design level is significantly reduced. If we have an R of 8 structure, we are designing for 1/12 of those MCE forces. I think everyone understands that when they use the R factor. Now let's look at the force versus displacement relationship for a structure. If we have an elastic structure, the force versus displacement relationship is a constant stiffness, and so you get a single slope on that line. And that's the elastic stiffness of the structure. If the structure remains elastic all the way up to that MCE ground motion acceleration, then we get a very large lateral load. But as we saw in the previous slide, we're only required to design for something that might be on the order of 1/6 to 1/12 of that MCE level acceleration. So this is the required strength, the required base shear strength of the structure. So the structure we know has to be within its design strength up to that level. Somewhere in between that required strength and that very high MCE force, we're going to get some yielding of the structure. And so if you follow the lateral load versus deformation profile of the structure, in other words, if you push it over laterally, somewhere above that required strength, it's going to start to yield, and yielding will progress. It may form plastic hinges in some beams and then form more and more plastic hinges, and as that yielding progresses and forms a full mechanism, we get to the maximum capacity of the structure. And that is represented by this horizontal line that we just drew at some level, at some factor times the required base shear strength. And that factor is the omega sub O factor, which is a reasonable guess for typical structures that are designed efficiently. There is some overstrength. And that reasonable guess, the omega sub O factor, is shown in this diagram. So the elements that are designed for the base shear forces, say the beams, or if you have a braced frame, it would be the braces, are the fuses of the structure. So these are the things that we want to yield in order to get inelastic deformation capacity. Once we form this mechanism, which is the desired mechanism for the structure, we want to protect other elements from having failure, for example, buckling of columns. And so those other elements, those critical elements are designed for the higher force, which represents what we think the maximum earthquake force that this structure will see, the maximum acceleration that it sees as it forms the full yielding mechanism. And and those elements are typically columns that we want to protect from buckling or other forms of failure. And also collector beams are designed up at this protected level. And the ratio between the design base shear and this omega sub O level is about 2 to 3. So the omega sub O is a load factor, but it kind of represents an analysis. It represents a guess at what a more sophisticated analysis would show as the maximum capacity of the structure. So our guess is for steel structures somewhere in the range of 2 to 3, depending on the type of system that we have. So the design of some elements for the omega sub O forces and the design of other elements for the E forces is the proportioning that we require in the seismic system. And a good analogy for that is a circuit with a fuse, with the yielding elements being the fuse, which we would like to be weaker than the rest of the structure, which is the circuit, so that when we get failure, which we think we will in an earthquake, when we get yielding, we have yielding where we want it, and we protect the elements that would not have high ductility. So in order to provide a seismic load path, we want, of course, a complete load path. We also want a proportioned load path. We want the yielding elements to control, so we want them to be decidedly weaker than the protected elements, and we also need those to be ductile. So the elements that we can make highly ductile, those are the ones that we designate as the yielding elements. And we want to protect the non-yielding elements. And the best way to protect them is through proportioning. And the more reliable our proportioning, the better we have protected these elements. So omega sub O is kind of a rough guess. You can also do a more sophisticated analysis to figure out what is the maximum force that those columns or collectors can see. So to complete that fuse concept, let's look for a moment at a concentrically braced frame. As I said, the fuses in this system are the braces. They will buckle or yield, and that's the sort of yielding that we encourage in the frame. So here's the desired mechanism, with the braces being the fuses, and here's the rest of the system leaning on to our lateral system. That's a gravity column and some collector beams. And what we want to avoid, in order to make sure that we have a good functioning seismic system, we want to avoid things like buckling of columns, so we will make sure they are strong enough. We want to avoid failure of collector beams as they deliver load to our frame, and also failure of connections within the frame. So all three of those things that we're looking at down below are designed either for the omega sub O level force or for the capacity of the frame. So we use that omega sub O or other capacity design requirements to prevent those three mechanisms shown at the bottom of the slide and encourage the mechanism shown at the top of the slide. All right, so understanding that, let's launch into load path. And this is a great diagram of a load path that doesn't quite work. The idea of a load path, or the definition that we should bear in mind, is a path that connects the point of application of a load to the point of resistance. And that's a very good concept when we're talking about gravity loads. It's very clear, and it's a good concept when we're talking about wind loads. It needs a little bit more nuance when we're talking about seismic design, because in seismic design, really the point of application can be considered the ground, and it's also the point of resistance. And so we do need a load path that goes from the point of application to the point of resistance, but also hits every mass within the structure to make sure that the mass does not move. So when we're talking about load path, here are the lateral. Here's the moment frame in this case, and that's the lateral load-resisting framing, and there's the gravity framing. If we have wind load, that's an external load, and the participating areas of the structure are those that are exposed to the wind. Seismic loads are not external. They're inertial. They have to do with the mass of the element. So all masses in the structure participate. And I love this photograph of the dog on the pickup truck. The force that the dog sees, of course, has something to do with the acceleration of the pickup truck. But if the dog happens to be on a frictionless surface, the dog will not see any force, but will fall to the ground. The force that the dog sees has some function with some relationship to the acceleration of the pickup truck, but also to the mass of the dog and how the dog braces itself as the pickup truck accelerates. So that's more the case of our buildings in seismic design. So starting with wind, wind is external. We can think of these particles of force that need to find their way through the system down to the foundation. So here they go. They find their way through the diaphragm into shear in the columns and work their way down to the foundation. So that's the wind load path. Seismic load path is a little different. We start with acceleration of the ground, and the force gets into the structure where the mass is, depending on both the mass and the dynamic characteristics of the structure. And then it has to, of course, find its way back down again. So you can think of it as kind of a motion back and forth. And every mass in the structure participates, whether it's the mass of a column, the mass of a beam, the mass of a diaphragm, or as shown here, the mass of, this is a large mechanical unit that needs to be anchored. Because if it is not connected, if it does not have a load path, it will not necessarily see an acceleration, but it will move with respect to the structure, or the structure will move with respect to it. So every mass needs a load path down to the foundation, even though, as I said, the load comes from the ground. Okay, so the magnitude of the force that each mass sees is a function of the ground motion, the mass of the item, building dynamics. So the same mass at the roof might accelerate more than at a floor at mid-height, depending on the characteristics of the structure. And very importantly, diaphragms represent a large percentage, sometimes the majority, of the building mass, or typically the majority of the building mass. The seismic load-resisting system includes the vertical frames. So here we see beams are part of it, columns are part, and sometimes we have braced frames, sometimes they're just moment frames, but where we have braced frames, those are obviously part of the vertical frames. Diaphragms are an important part of the seismic load-resisting system. Chords and collectors within the diaphragm are very important, and we'll talk about those a little bit later. And collectors, or sometimes called drag beams, and the deck of the diaphragm, I should have mentioned. And foundations are an important part of that load path. The load path has to be continuous. So if you imagine, if you just place your pen anywhere on the diagram of the structure, if there's mass there, there has to be a connection. There has to be a load path from that mass down to the foundation. So continuous load path here, it's working its way through shear in the deck, then through a collector beam, then down through the braces, and there's a change in direction there at where the brace delivers the load to a beam and the beam to another brace, and so on. So that's the load path down to the foundation. Now this load path has a few changes in direction. Wherever there's a change in direction or an eccentricity, there's going to be something akin to a moment. So if you think of this diaphragm here, the roof diaphragm is spanning between a moment frame on the right-hand side of the structure and another one on the left-hand side of the structure. You have some bending in that roof deck diaphragm. And that bending will manifest itself in tension and compression at the extreme fibers of that deck, or in the chord members at each end of that diaphragm. So that eccentricity between the mass in the direction of acceleration here and the lateral resistance causes something that we think of as flexure. Similarly, there's a vertical eccentricity, again, looking at the force that the roof diaphragm sees. That force in the vertical plane is eccentric from the foundation, and so there's going to be overturning, which is again akin to moment. And wherever there's a change in direction, for static equilibrium, there's another force that needs to be accounted for. So if we look at this connection up close, we have the horizontal shear being carried as a diagonal force in this brace. The horizontal component gets carried over to another brace, but the change in direction manifests itself in a vertical force in that column. Where we have offsets in the load path, here shown as an in-plane offset, but it could be out of plane just as easily, we're decomposing the shear in the frame from the overturning moment, and we need to follow each separately. So the overturning moment goes down, and we need to account for that in the design of these columns. And the shear gets dragged out, in this case, in the plane of the frame, out to another frame in plane, but again, it could be out of plane, in which case it would be shear in the diaphragm. So we arrive now at foundations. We can have shallow foundations or deep foundations, and they have a lot of the same issues. They need to provide support. They need to provide, that's vertical support, lateral resistance, stability against overturning. So starting with the shallow foundations, we get overturning moments at the frames, and that causes uneven bearing pressure. And the bearing pressure that we're allowed to develop is going to be limited based on the capacity of the soil. We should be looking at short duration increases in resistance, and geotechnical engineers will typically put that in their investigations, and it might be something on the order of a 1/3, 1/2 increase depending on the soil conditions, but certainly you get a lot more strength for short duration loads as we have in seismic response. For purposes of our calculations, we often idealize that as triangular, but we don't have to. You could also model with soil springs. Very importantly, you want to make sure that you're not developing significant tension in the springs in such a model, because the soil typically doesn't have much in the way of tension strength. Lateral resistance, so-called sliding. There is friction at the bottom of these shallow foundations. There's also bearing pressure that builds up at the faces of these footings. Sometimes we're permitted to account for both simultaneously. Sometimes the force deformation characteristics of the two are not quite compatible, and so we're not allowed to do so. Where we have problems with lateral resistance, we have a common strategy is to reach out and grab more footings in order to get more lateral resistance, say friction on other footings under gravity columns. And so you might end up with a foundation plan that looks like this. And it's even though sliding or friction is the way that the lateral forces get into the building, you do need to provide resistance to that sliding, at least to control any relative movement between one footing and another. If all the footings are tied together as one big mat, arguably the shifting of the soil underneath the building is less problematic than if you have isolated spread footings and your braced frame moves differentially compared to your gravity columns. We also have to design for stability, and this is kind of an area where the building code doesn't provide a lot of direction. So we have the possibility, if our footing does not weigh as much as the maximum forces that our frame can develop, we have the possibility that we will get some uplift in that footing, and that's a nonlinear effect that's very hard to evaluate using elastic analysis. Per ASCE 7, the minimum required mass of that footing can be calculated using ASD load combinations. So you could end up with a footing that, if you evaluate it using ASD load combinations, is stable, but under LRFD load combinations has a different condition. As the footing approaches the limit state of instability, you get larger and larger pressures under the toe of that footing, and at some point you may exceed the bearing capacity of the soil, and then you have locally some settlement. So if we have a foundation that is significantly lighter than the force that the frame can develop, you could have rocking as the governing mode. That will tend to produce less ductility demand in the structure above, but larger displacement. So if the footing is relatively light, you get some uplift, which is something that is difficult to evaluate using elastic methods. It's not always. It's arguably beneficial in some respects for the structural response, but it's hard to quantify what the displacements are that develop. Looking at deep foundations, we have overturning at the frames. Our piles and piers may have end bearing, they may have friction. In many cases, we may be looking at say piles that are designed only for end bearing, but actually have a lot of frictional resistance as well. And so you, especially with deep foundations, you can develop a lot of overstrength in the foundation that you may not be considering in your calculations. In tension, typically we rely just on the friction of those piles. And these forces are also likewise subject to short duration increases, because it takes a bit of time to cause significant movement in the soil. Lateral resistance, if we have extremely poor soil, we rely on the piles in shear and bending rather than the capacity of the soil in bearing, but there typically is significant capacity in the soil in bearing. If we, for design purposes, if we run into trouble with insufficient resistance, we can reach out and grab other piles and piers and create a sort of ground floor diaphragm to engage all the piles under a building. That's not uncommon for buildings in bay mud in San Francisco to utilize every single pile. And in some areas, batter piles are common for resisting some lateral forces. And here's a system of grade beams reaching out and grabbing multiple piles. Again, we have the issue of stability. The maximum overturning that the system can see is probably limited by the capacity of the piles. But not the shear resistance in the soil, but probably the reinforcement between those piles and the pile cap. And so some engineers will use the overturning of the frame to limit the forces that can be seen. For the deep foundations, it's probably not a good idea to count on movement of those foundations at all. Because there's, as I said, a lot of overstrength that exists in those deep foundations. Diaphragms. We'll talk about different types of diaphragms and then the roles of diaphragms. Common diaphragm is just a steel deck that is either welded to steel framing or connected with screws or shot pins. The shear is handled in the deck, and then the cord and collector forces are in the steel members. That deck can be stiffened with a concrete fill, and again, the shear path has to be the shear has to be in the deck and transmitted through the fasteners, whether they be welds or it could be here studs or screws or shot pins. The strength of the steel deck itself is increased by having the concrete fill to stiffen and prevent buckling. However, the mass is significantly increased also, and so the shear demands are much larger. And again, the steel framing is used as cords and collectors. When we have a reinforced composite deck, the shear typically we assume is in the deck, in the reinforced deck, and we, in relatively simplistic terms, we might simply take the concrete above the top flute as a reinforced concrete member and calculate the shear strength of that. The transfer forces into members of our braced frame or moment frame may be through shear studs, and we may also use the steel framing as the cords and collectors, in which case we need to accumulate the forces through those studs into the cords and collectors as well. We could also use reinforcement in certain zones as the cords and collectors, and we'll talk about that in a little bit later on in this section. And finally, we can have horizontal truss diaphragms. So here is an industrial building. You can tell that because of the crane on the crane rails. And the stiffening and strengthening that roof diaphragm are a couple of trusses here, one outlined in red and the other one outlined here in yellow. And those trusses are taking the shear and bending of the beam-like behavior that we discussed for the diaphragm, and essentially relieving that work from the deck. So the shear is handled in these diagonal members. We have steel cords and collectors, and the deck that we have up above is really only for gravity. So we'll talk about the role of diaphragms, some components, some design aspects, and building analysis, as well as the internal forces in the diaphragm. So this is from a NIST publication. We have a reference to that at the end of this seminar. And it's a little diagram of a steel building that has a number of things going on with the diaphragms, including the diaphragm supporting gravity, delivering forces to our lateral frames, providing stability of our gravity columns, transferring forces between one frame and another, and resisting our P delta thrust. So starting out with the inertial forces, here at the top we have our diagrammatic loading of the diaphragm as a distributed load. This would be for earthquake motions in the up and down direction of the slide. And that load gets delivered to our frames, and we have a little bit of torsion going on here, in that we're developing forces in the frames that are orthogonal to the application of load. And the way that these forces get to the various frames shown here is through shear and bending of the diaphragm. So very important function of the diaphragm. And here we have a diagram of a building, and we have a gravity column at the corner, and we're designing that gravity column with an effective length equal to 1 story height. And the reason that we're able to do that is that the diaphragms hold that column in place and essentially use the stiffness of the braced frames elsewhere in the building, or they could be moment frames, but use the stiffness of the lateral system to hold the column in place so that it will not buckle over several stories, but if it is overloaded, it will buckle between one story and the next. So the diaphragm is instrumental in providing that lateral bracing. When the building moves, as shown here, let's say under significant lateral load, the gravity forces that are delivered to this column, so here are the pass-through forces from the level above, just going down the column, but the gravity force that's delivered at that level, that's a vertical force. And that vertical force has to change direction to become a diagonal force in the direction of the column, which is now sloped due to the building drift. And that little change in direction creates a little horizontal thrust. And that happens at every level. So you look at that gravity column, and at every level, the vertical force needs a little bit of diagonal thrust in order to follow the diagonal line of the column. And that thrust works its way through the diaphragm and then gets delivered as an additional lateral load to our frame. So in addition to the lateral load that caused the displacement that's shown here, the P delta thrust at every gravity column adds to our lateral load. And then where we have changes in stiffness, or perhaps even removal of frames, the lateral load that's in one frame may want to migrate to another based on the difference in stiffness. And so transferring forces between one frame and another is an important role of the diaphragm. And so when you look at, and this is waterfront in New York, where for a variety of reasons, setbacks have been a very important part of the design of buildings in New York. Wherever you have these setbacks, or where you have a podium structure, there is a tendency for lateral loads to redistribute based on changes of where the mass is, and also changes in location and number of frames. And so especially for taller buildings, there's a lot of redistribution of forces from one frame to another, especially when there's some sort of geometrical change like this. Another common system is a combination of a wall and a frame. The wall could be used in the core of the building, the frame, the perimeter. And these systems have different displacement profiles, but when you put them in the same building, the diaphragms will enforce similar displacement between the wall and the frame. And the diaphragm then has to transfer a lot of forces back and forth between the wall and the frame in order to get them to move together. And so the transfer forces in this type of dual system can be quite large. Even when you have just different frames with different proportions, you get significant transfer forces. Not as large as in the dual system, but still significant, and that will impact the design. And then finally, this is very important for taller buildings, there's what is often called the backstay effect. So here we see a wall or braced frame in the center of the building. And if you simply ignore or isolate the building from the retaining walls at the basement, you deliver a pretty large overturning moment at the base of that wall or frame. And so you get a moment diagram that conceptually looks like this. And often those are very, very large overturning moments, very expensive to design for. So anything we can do to reduce that base overturning moment might be beneficial for the economy of the structure. And one thing that is often done is to take out a portion of that overturning moment in a horizontal force couple like this. So some of the force is taken out there at the ground floor level shown here, and then the horizontal force couple is responsible for some of the base overturning moment. So the modified moment diagram then has a bite taken out of it, and that bite is what goes into the horizontal force couple. And constructing the shear diagram that corresponds to this moment diagram, it looks something like this. You need a shear reversal to start moving the moment diagram in the other direction. Now that shear reversal is very important because it represents a huge force going into that backstay diaphragm. So that force can be larger than the base shear of the building. There are there's a lot of there are a lot of discussion in the literature of different things a designer can do to control or address these large forces, and perhaps the magnitude of force that you can actually take into your backstay diaphragm will dictate how much of the overturning moment you can actually resist in this horizontal force couple. So that's an important function of diaphragms, especially for taller buildings, buildings that have this sort of basement condition, or buildings that have a podium and then a tower also have this backstay effect. Let's talk a little bit about the diaphragm components here. Here's the diaphragm. The loading, we'll call it north-south loading. Shear is in the deck, and then we're accumulating forces in these collectors on the east and west end of the buildings. And this happens to be a moment frame, and shear is taken by the 4 columns of this moment frame. And so we get a collector diagram, a collector axial force diagram that looks like this. And we also have the shear in the deck, not only loading the collector, but it's also loading the chords at the north and south. And as it loads those chords, it creates axial forces that have a axial force diagram that looks something like this. So the perimeter members in this frame are chords or collectors, or in this building configuration. When we change the direction of loading, we still have the deck working in shear, but these perimeter members now become collectors, and this happens to be a braced frame layout like this, where the shear is taken out at those 2 points where you see the big discontinuities. And then the east and west members are working as chords. They have very small forces because of the depth of this diaphragm and the shortness of the span. Nevertheless, they have those chord forces as well. Now, we need to consider for diaphragms the rigidity of the diaphragm in order to understand what role the diaphragm plays, or how the diaphragm plays its role within the overall building load path. A flexible diaphragm is one in which the flexibility of the diaphragm is, say, an order of magnitude beyond the flexibility of the frame. So for our purposes then in analysis, we can consider the diaphragm to be flexible and supported on rigid supports. At the other extreme, we can have a diaphragm that is very, very stiff, and frames that are perhaps an order of magnitude more flexible than the diaphragm. So whatever deformation the diaphragm undergoes due to seismic accelerations is negligible compared to the deformation that, say, these moment frames represented by springs undergo. And we can consider, for analysis, for purposes of analyzing the building, we can consider the diaphragm to be rigid and just worry about the relative flexibility and position of our different frames. Now, in between that, we might have a diaphragm whose flexibility is comparable to the flexibility of the frames, in which case for building analysis we are told we need to consider simultaneously the flexibility of the diaphragm and the flexibility of the frames. And we call that diaphragm semi-rigid. It is a finite flexibility, something that we can put in a three-dimensional building model. And the difference between these diaphragms really can be drawn like this. The flexible diaphragm can be treated as a determinate system, where you start with loads on the diaphragm and simply follow them through the load path. Whereas the rigid and semi-rigid diaphragms really have to be considered indeterminate systems, where we need a model that includes flexibility of at least some elements in order to figure out where the loads go. And there is, of course, a case where you have only 3 lines of resistance where it's determinate regardless of whether your diaphragm is rigid or semi-rigid. Okay, so if we have a determinate diaphragm, let's say the flexible diaphragm, we can analyze the diaphragm. So we begin by applying loads to the diaphragm. We analyze it. We get our reactions, and those are the loads on the frames. And then we can proceed with the design of the frames. If we have an indeterminate system, that is to say a rigid or semi-rigid diaphragm, we have to do it in the reverse order. We have to analyze the building, create a three-dimensional model that has the appropriate stiffnesses for the lateral load-resisting system elements, the flexibility of the frames, and for a semi-rigid diaphragm, the diaphragm flexibility as well. And in a three-dimensional model, we solve for the forces that go to each of these frames, and then we can use the forces in the frames to figure out what is coming from the diaphragm at each level. So we'll start with the flexible diaphragm, which is the determinate system. We get our load, which is the diaphragm load here. We can calculate it as a single force, but we have to treat it as a distributed load, and it's distributed as the mass is distributed. So for a rectangular diaphragm, it's a uniform load, and we get a shear diagram, two triangles as shown here with reactions where the walls or frames are, and a moment diagram that looks like this at the bottom, and that moment diagram is used to determine the chord forces. Now, a flexible diaphragm does not mean simple span. That's a mistake that a lot of people make. A flexible diaphragm, if you have multiple span conditions, can be solved the same way you do a multiple span beam, and a cantilever condition the same way you treat a cantilever beam, and you get different sorts of moment diagrams. Now for these two last conditions, those moment diagrams go to zero at some point. I strongly recommend that no designer ever assume that you know exactly where it's going to go to zero, or put in anything that has zero axial force capacity on those chord lines. Instead, you can draw envelopes around these. And of course, you have to remember that the seismic loads are reversible, so you have to treat these loads as these diagrams as reversible as well. So you might draw envelopes around this moment diagram, such as I've shown, and provide capacities for the outside of those envelopes. Okay, so here's our distributed load, here's our shear diagram, our collector forces, and our chord forces. That's our typical diaphragm analysis based on an assumption that we have uniform shear in that diaphragm. So if you look at little rectangles of the diaphragm, your shear increases as you move from the center of the diaphragm out towards the frames, and still assuming uniform shear, you get uniform shear along the east and west walls, and you also get that shear contributing to the chord forces at the extreme fibers. Okay. Now you could also do an analysis, make an assumption. Either way, you could determine that the shear is not uniform along the collector length. And any sort of analysis will show you that that's probably true, that it will never be perfectly uniform. We might assume it's uniform for design purposes, but in other cases we might assume that it might be convenient for us to assume that it's non-uniform, as shown here. And that's fine as long as you follow through the implications. And one of the implications are these local chord forces that need to be resisted. So because we're concentrating the shear, we can't assume all of that chord force instantly finds its way out to the extreme fibers. Also, we need to tie our diaphragm together. This may not be a big issue for a composite deck with reinforcement, but if we have just bar joists with a steel deck on top, we do need to make sure that we can provide a load path, as shown here with these little blue arrows, to make sure the deck does not pull apart. So for design purposes then, we need to look at this heightened shear, which is our assumption, look at our chords, and look at the local forces as well. When we have non-flexible diaphragms, one thing that we find is that the forces are are resolved, including some participation of the frames that are perpendicular to the direction of the application of loading. So here we have our applied load at the top, and we have a shear diagram drawn like this just based on the two walls or frames oriented to resist the load, but we also have some force going into these orthogonal walls. If we draw a moment diagram based on this shear diagram, well, we have a problem in that we have the moment doesn't go to 0 at the end of the diaphragm. So we know that's not right. So we need to correct that moment diagram. And here's this moment correction that I'm drawing, which corresponds to a chord force, or I should say collector force, but a collector force for this chord member at the north or south of the diaphragm. And so that represents what the orthogonal frame is doing. And so when you add those two together as an axial force diagram, you get behavior that looks like this, and it does go to 0. So the missing moment is what's taken up by these perpendicular frames or walls. And that's an important thing because when that member is acting both as a chord and a collector for this orthogonal component of the motion, your forces will of course be larger and should be designed for. When we do a three-dimensional analysis, often the chord forces are not really all that great compared to the collector forces, and something you find based on the configuration. But if you do a three-dimensional analysis of a building with a footprint that looks like this, as opposed to a long span big box store, you'll find that the chord forces are actually quite small because we're not asking the diaphragm to span very far. And so what we can do when we do a three-dimensional analysis of a rigid or semi-rigid diaphragm system, we can get the reactions at each of these frames. So the difference between the force in the frame above and the force in the frame below is what's coming from that frame, and carry those over to a diaphragm analysis. And for purposes of the diaphragm analysis, what is typically critical is simply taking that force and dissipating it, treating our collector as a dissipator, and figuring out how that force can get into shear in the diaphragm. And once you get it into shear in the diaphragm, you can solve for the chord forces that correspond to it as well. And so that's a typical approach that's done using a three-dimensional analysis. But it gets a little bit tricky, as I will show in a moment. So collectors are collectors, such as we've shown here, as we discussed earlier on, are a protected element. Our collectors could be reinforcement in the composite deck, or they could be steel framing. The diaphragm forces are modified in ASE 7 compared to the vertical force distribution. And this is what I was talking about just a moment ago with respect to that three-dimensional building analysis. So here's the equivalent lateral force diagram. The profile of those forces is roughly triangular. But we also have minimum diaphragm forces. And the reason we have minimum diaphragm forces is the equivalent lateral force procedure is really based on getting shear and overturning moment for the frame. It is not based on getting the accelerations at each level, and that's the job of the diaphragm force. Now we've got a problem here in that we have this acceleration of the diaphragm giving us the force that's acting on the diaphragm at that level, but we also have transfer forces that might be happening at the levels above, and so we need to somehow combine the two. So that's the equivalent lateral force set of forces. These are the diaphragm forces shown in color. And the way to do it, if you want to do it in a full building analysis, the way to do it is to replace the force, say the second floor force, replace it with the minimum diaphragm force, and then you can consider the forces above, but the forces above are considered only for the force that's transferred through that diaphragm. And the same goes at every level. You don't need to consider the forces below, only the forces above. And the forces above are only considered insofar as they lead to transfer forces within the diaphragm. And depending on your layout, your transfer forces may or may not be significant. And you can look at your results and figure out how much your building analysis results and figure out how much transfer force there is. And there are different methods, to use to manipulate the results to get this information out of a single analysis. When we look at combining these forces with the capacity design requirements that we have for several systems, there's a fairly efficient method that I'm going to show here. Down below in blue, we can calculate the capacity of the frame based on the maximum tension and compression capacities. In yellow here, we have the diaphragm force, the minimum diaphragm force that we have to design for. And up above in red, we have a force that comes from the analysis. Now these things won't necessarily add up. The sum of the horizontal forces won't necessarily add to 0. And so what we do is we arbitrarily bump up the forces shown in red from the analysis by an overstrength factor. So now we've adjusted them to be statically consistent. And that overstrength factor, we can back solve for that overstrength factor using this equation. And it's a way to manipulate your forces so that they're statically consistent, so you can design for that diaphragm force and design these connections that have multiple members coming in and maintain static equilibrium. Okay, and then you can proceed with the design of that collector line consistent with the capacity of the frame below. As I said, the reinforcement within the deck can be used as a collector. This typically requires some width of deck to keep our stresses low. Stability of that deck is typically not critical. When we use a width of that deck, if the frame is at the perimeter of the building, there's going to be some eccentricity. And that eccentricity is going to cause a little bit of local moment. Local chords need to be placed there to resist that moment. And there's going to be a concentrated shear transfer as shown in this diagram here. So here's a plan layout. We have braced frames at either end, and these yellow lines represent reinforcement that we're going to use as our collector to deliver forces to this braced frame. So looking at that in some detail now, looking at this diagram, there are a number of things going on. First of all, our collector force. As we discussed at the beginning of this seminar, we need to consider the amplified seismic load omega sub O times E. That's the first thing. And then in order to keep our concrete stresses low in this composite deck, we're going to have an area that keeps our concrete stress below 0.5 F prime C because it's unconfined concrete. So we solve for the width that we need in order to keep the stress low, and that gives us the width of the collector zone that we're going to use. That's for the compression. We might as well use the same for the tension. And based on that width then, we have an eccentricity which is about half that width. So that eccentricity, E, is about half the width. And therefore we have a moment which is equal to the collector force times the eccentricity. And that moment is going to be taken out in local chords represented by these blue arrows with the C. And those local chords are going to have a force that you can get from this equation. It's the moment represented by the eccentricity times the collector force divided by the distance between these local chords. So once we've provided strength both within the collector and within these local chords, and of course the local shear transfer into the braced frame beam, then we have a system that works. We'll talk a little bit about the design strength of collectors here. Collectors are beam columns. They are beams for resisting the gravity load, and they are columns in that they have axial forces due to seismic load. So this would be using the steel member as the collector rather than reinforcement in the deck. So the compressive strength is where it gets a little bit tricky. The flexural strength, it's the same as any other beam in the system. So here I'm showing a wide flange beam that has discrete lateral and torsional bracing. So it may not have much in the way of a deck above it all. The compressive strength could be governed by major axis flexural buckling over the full length, minor axis flexural buckling between these brace points, or torsional buckling between these torsional brace points. But as a reminder, the minor axis flexural buckling is always going to give you a lower force than the torsional buckling for the same unbraced length for a wide flange. So we usually ignore the torsional buckling. Now if you have a composite deck like this, well, a couple of things are going on. One, you have continuous lateral bracing of the top flange. So really, you still could get major axis flexural buckling. Minor axis flexural buckling can't really happen, but what you have is a sort of mixture of minor axis buckling and torsional buckling, and it's called flexural torsional buckling. And it's a constrained axis flexural torsional buckling in that the top flange can't move. So here's a diagram of those different modes. This would be minor axis buckling. The whole section moves laterally. This is torsional buckling. It twists about its centroidal axis. And then constrained axis flexural torsional buckling. It twists about that point of restraint. So for that calculation, if you wanted to do constrained axis flexural torsional buckling, you could use a piece of E for chapter E purposes calculated in this way. And all of those are section properties really, except for the length, the KL of the section, and this dimension A, which is the dimension from the centroid to the point of restraint, which would be the top of the top flange. So that would really just be D over 2. So this gives us our constrained axis flexural torsional buckling strength if we want to do that calculation. Most building analysis software packages, I believe, do not do this, but they will do the minor axis buckling instead. Also, one thing I'm not showing explicitly here that you could do is you could count on the web stiffness and slab stiffness to give you a continuous torsional bracing. And I hope we develop methods to do that, because we'll probably see that these collectors are stronger than anyone believes they are at the moment. This is a table from the Seismic Design Manual showing how you can calculate the axial strength of such a collector in different conditions: steel deck, composite deck, or horizontal diagonal bracing. For ribs parallel to the beam, you could have torsional buckling or minor axis flexural buckling. And as a reminder, minor axis flexural buckling is always going to give you a lower strength, so you can pretty much, for a wide flange, so you can pretty much ignore torsional buckling. And same goes for the diagonal bracing here. For the other two, for composite deck, for example, the torsional buckling really doesn't apply, but we do have constrained axis flexural torsional buckling. Minor axis flexural buckling doesn't apply, but if you did that calculation, you would be conservative, and you could do that in lieu of the constrained axis flexural torsional buckling. And so that's what most people and many software packages do. For the flexural strength, if you've got a composite deck, fully braced, steel deck with the ribs perpendicular, you're laterally braced, ribs parallel. Generally, I think people consider that to be unbraced by the deck, but braced by perpendicular framing. Collector connections, we have gravity forces and seismic simultaneously, axial and rotation. So looking at the forces, if we're using the beam as a collector, we're also using the beam connections as collector connections. And so there's that horizontal force simultaneous with the gravity force. All of those limit states to check, and now we have some sort of diagonal resultant on those forces. The way that this is typically done is to get our strength, say this is a single plate connection, our strength from the manual. For the vertical forces, we can check the same limit states horizontally and simply do a square root of the sum of the squares of our demand to capacity ratios. We also have a rotation demand as part of these connections. That as we deform the frame laterally, we're imposing a rotation. A single plate connection has very large rotation capacity. So does you can also use the extended plate method for a double column of bolts if you need more strength. When we get to higher forces, some engineers use a welded top flange, which is a good method. It does introduce some eccentricity. Or you can weld both flanges, in which case you have essentially a moment connection, which will attract moments. If you have large drifts, you will have ductility demands, and you can detail that for a moderate level of ductility. Also importantly, where we have frames that have significant vertical distortion, shown here, we can have significant rotation caused by the addition of lateral drift and the vertical deformation of these braced frame columns. And so that has to be accounted for. That may result in larger rotations than would otherwise be necessary. Our typical connections from the manual, of course, have large rotation capacities. And this gets us to the issue of deformation capacity. We'll talk about its necessity, what happens to connections, some other issues including stairs and pounding, and some critical conditions. So here's a diagram of a moment frame undergoing large drift. And you can see that there's a lot of rotation in that moment frame, but the gravity system has to undergo the same distortion as well. So our performance expectation for the gravity system as we go out to large seismic drifts is that we will prevent collapse, both global and local. It's not that we will maintain all connections to be elastic. That's not even our performance goal for service loads. So here's a diagram, or here's a photograph of testing of a single plate connection at UC Berkeley. I think this testing went up past 10% rotation. And so these connections, as I said, have a tremendous rotation capacity. So unless you're dealing with an archaic building, if your steel connections will have very good rotation capacity for seismic drifts. So the single plate connection, double angle connection from the manual will get you out to your maximum allowed seismic drifts without any problem. So these connections are typically detailed so that they have 3% rotation capacity with the design range. And then when you add some seismic drift on top of that, that can be accommodated and still maintain the integrity of the connection. Where we have flexible diaphragms, say we have a big box store, we should be aware that there's some extra deformation required, extra slope, extra P delta effect, and the like, where the diaphragm is contributing significantly to the lateral displacement. So that would be increased rotation, increased P delta effect. Stairs are very important. I know this. I know we're talking about the load path, and now we're going to talk about something we don't want on the load path. The stairs, because of their diagonal configuration here, they want to act as braces, or if we don't do anything about them, they will tend to act as braces. And that's a problem because we're not detailing them for ductility, and we don't want them to have ductility demands. They're very stiff, they're not very ductile, and after an earthquake, we want to be able to evacuate the building. If there are people injured, we want first responders to be able to go up the stairs and investigate. So we really want to protect the stairs by removing them from the load path. We need to detail to allow some movement. So an approach that's, and not only allow movement, but maintain gravity support even at that movement. So an approach that a lot of people take with stairs is to tie them in hard, as we say, tie them in so that they move with one end, but tie them in flexibly with some motion allowed at the other end. So here at the bottom end of the stair, I'm showing an angle connection with a slotted hole, and at the top, that may be a fully welded hard connection. So the stair will move with the upper diaphragm where this ground floor slab stays in place. Now there's also displacement in and out of the page, as we see here, and sometimes the stairs are flexible enough to handle that without any special detailing, but that's also something that should be considered by the designer. So as we get motion, and hopefully this isn't too jerky for anyone watching, but you can see that the stair moves with the upper diaphragm and it's moving back and forth within that slot. Additionally, since seismic drifts are somewhat hard to predict, we may be underestimating that maximum seismic drift. And so we want to consider what would happen if the drift is larger than the slot that we've accommodated. And so in this particular case, if we shear that bolt, that's not a big deal. So if we make that a relatively weak connection so that we don't tear up the gravity support at the upper end, I think that's probably the best approach. And in this ground floor slab situation, we maintain the gravity support at the bottom, so that's not a problem. Pounding is another issue, somewhat similar, that the displacement of the system can result in some special demands. So it's a dynamic effect where you have impact between two structures. These may be adjacent buildings on adjacent lots, or there may be a seismic separation within a building. But as the buildings move somewhat independently, perhaps with different dynamic characteristics, they can have impact. And this is especially problematic where you have unrelated buildings and they might have different story heights. And so one building might hit another building not at the deck level, but perhaps mid-height at the column, and that would be very problematic for that column. So very important to maintain proper separation between buildings where you have this condition. A critical condition that addressed really for the first time in the ASE 7-2010 is a member spanning across a seismic joint, as shown here. So you could have different dynamic characteristics on each side of this seismic joint, and you need to maintain the gravity support at the corbel of that member spanning across. This is a very high consequence condition, meaning it's not just a question of how big a separation you get. It's a question of whether the bridge is standing or falling into the atrium. So loss of gravity support is something we do not want to risk. Loss of egress is also a problem. So that support on the bracket we're going to treat very, very delicately. So that extra care is in a couple of different ways. Mainly it's in estimating the upper bound displacement. And then instead of doing a square root of the sum of the squares of displacements, we take the absolute sum of the displacement of the building or the structure on the left and the structure on the right. So here's a diagram of that bracket condition. You see the plate spanning over the seismic joint. We're making the estimate that the maximum displacement of each of these, instead of using just the design story drift, we're multiplying by 1.5. That's a correction of that 2/3 factor we saw early on in the seminar. And we're also correcting by the ratio of R over C sub D. So instead of amplifying our displacements by C sub D, we're effectively amplifying our displacements by the R factor. And then we're going to take the absolute sum. We're going to assume the structure on the left can move its full displacement, and the structure on the right can move its full displacement. The separation is it's probably a good idea. The gap, I'm saying, between these two diaphragms is probably a good idea, but the main thing is maintaining support for that maximum separation. So for purposes of that bearing length, we need to calculate the bearing length that we need and add to it the expected relative separation of these two. So that's a very big corbel. And so these two structures, as I said, they may have different periods of vibration, and so you could get movement independent that looks like this. There's a condition where they're both moving together, and that's the critical condition for pounding. And so we've made the gap big enough so that we don't anticipate pounding even under these maximum motions. And then they could move apart, and that is the critical condition for the bracket. So you will have the maximum eccentricity on this bracket, and you need to make sure the bracket is designed for that condition. And it's also the critical condition for the joint cover, the maximum span that that joint cover has to see. And every time I've showed this slide to anyone at AISC, they always say, well, don't you really need a stiffener there? So there's your stiffener. And with that, we're ready to summarize what we've covered today. First of all, we need a complete load path to maintain our stability for lateral loads. The seismic load path has to pick up every mass in the structure and have a continuous load path down to the foundation. Also, the seismic load path has to be proportioned so that we promote yielding in these fuses, which is where we want our ductility demands, and we protect other elements from yielding, a very important aspect of the seismic load path. Foundations and diaphragms are an integral part of that seismic load path and need to be considered in the lateral load design. And the entire structure has to deform along with our lateral load resisting system. And then I always like to list a few additional resources. If you want to dig in deeper into diaphragms, we have this published by NEHRP, a free download, this technical brief on diaphragms in steel frame systems. And there's a lot of discussion of all of these issues in the AISC Seismic Design Manual. So with that, we arrive at question time.
All right, thank you very much, Raphael. And we do have a few questions. I would encourage you, anyone in the audience who has questions, feel free to submit those into the chat at this time. But we'll go ahead and start with the questions that we have. I want to go to slide 65 first, Raphael.
All right.
This is a question in regards to the moment correction calculation. And the question is, how was the moment correction calculated for the rigid diaphragm analysis here?
All right, so to walk through this process a little bit in a little bit more detail, we start with the shear diagram here where the reactions at the left-hand and right-hand side correspond to the forces in the two frames shown in the diagram down below. So those are reactions. That gives us our shear diagram, and that gives us the red line that gives us some additional moment here. And depending on which side, which end of the diaphragm we start at, we don't get to zero in the moment diagram. Now, the reason that we don't is there's some moment represented by this force couple in the orthogonal frames, shown here and here. So that force is a collector force. If we take let me take this red line here, and let's assume we've divided that red line, which is the moment in the diaphragm, by the depth of the diaphragm, and that gives us the chord force that we would be ordinarily expecting at the north and south of this diaphragm. Now, the force that's going into this frame, we can call that a collector force. And we can draw we can draw that as a vertical. Here I'm showing it sloped because it's a shear wall. It takes whatever 10 or 20 feet for the force to develop into the shear wall, and that we can draw that as a collector force, as if the moment at the end of the diaphragm here turned into that unresolved axial force at the end of the diaphragm turned into a collector force being dragged back to this shear wall. And so when you add the two, you get a force diagram that kind of makes sense for the chord here, where it gets to 0 at each end.
Okay. Let's go to slide 94, please. And this is regarding the stairs. I guess it's a two-part question. Is it always necessary to have that slotted connection for these stairs when you're designing for seismic resistance? And maybe further to the question is, do you have any suggestions if you have hard-connected stair designs in place?
All right. So the necessity of having a slotted connection here really depends on the lateral system and also on the stair system that you have. If you have a wood-framed house, you've got probably a fairly compatible system all the way through. That your shear walls have some flexibility, but your construction of your stair, it's continuously supported, nailed into a wood wall, and it's really not something to worry about. If you have, at one extreme, you have a very rigid system, say a shear wall system, concrete shear wall, or even a steel plate shear wall is fairly stiff. You could have relatively small displacement demands for that stair, and so you may not have to worry about the relative movement of one floor versus another. But if you have a relatively flexible system like a moment frame, then yes, you do need to be able to accommodate those displacements. And I think this is not something new to the industry. The detailing of typical stairs, I think, at least in California, has allowed for this sort of relative movement for pretty much my whole career. Now, if you have a building that was designed in 1950 in St. Louis, and probably in 1950 in St. Louis, people weren't thinking too much about large seismic motions, and nowadays, if you're designing in St. Louis, you are. That may be something that is problematic. It may not be the most problematic thing about that structure, but it may be problematic. And the remedy, I don't think there's a standard remedy for that at all. In some buildings, in retrofit, where there are a number of things that have very little displacement capacity, the best approach is to stiffen the entire system so that the displacement demands on those elements aren't that great. So for retrofit purposes, it's often very difficult to catalog and address all of the things that need extra displacement capacity and fix those, as compared to reducing the displacement demand by adding very stiff elements.
Okay. Let's move to 97, please. Okay. Can you provide an equation? I'm sorry. On this slide, you do provide the equation for calculating your delta sub M1, which appears to convert to an inelastic drift with the C sub D multiplier. it looks like you're converting an inelastic drift to an elastic drift by virtue of dividing by the C sub D value. Why are you converting to an elastic drift here?
Yeah, that's a good point to clarify. So what we're doing is we're dividing out the C sub D factor, but then we're multiplying by R. So it's as if we're saying, instead of using a C sub D of 5, or 5.5, let's say, for a special moment frame, use a C sub D of 8. Use the same C sub D as the R factor. So what we're effectively doing is increasing the C sub D factor so that it is equal to the R factor.
Okay. Question regarding industrial structures. In the case of a structure that's supporting a bin, what is your suggestion for diaphragm analysis?
Okay. I guess I'm going to have to plead ignorance on that. I'm not sure what the special characteristics are of a bin. I assume it's a concentrated mass that we're concerned with, and the issues there are load path. I think providing a load path from that mass to the lateral system.
Okay. And then a question regarding coming up with your shear and dependent on different R values. Can you, I guess it's kind of a pretty wide range question, but what are your thoughts on determining whether you go with a special versus ordinary system in taking the hit for a lower R value versus reducing your forces with a higher R value?
I think there's, I may be betraying my West Coast bias, but I think we know so little about the magnitude of seismic demands that I feel more comfortable with a more ductile system in that the variability of the seismic demand there really plays itself out in more or less ductility demand, more or less rotation of a special moment frame connection, as opposed to success or failure of something that is more brittle and has a lower rotation limit. So that's just a West Coast bias. I think a lot of people will look at very carefully at the cost implications of each, and that's, there's a lot of information that is useful for making those decisions. For cost purposes, I think you need to consider not only the tonnage of the system, but you have to consider for the expenses for the special systems, you have to consider inspection and perhaps erection time. And for the ordinary systems, you have to consider the cost of foundations and the cost of foundations and the cost of the rest of the system that has to be designed for the higher accelerations. So that's about all I'll say on the cost issue at the moment.
Okay. Well, thank you very much, Raphael, and thanks again for a great presentation. We need to wrap up today's lecture. There are a couple more unanswered questions, and we'll work with Mr. Sibeli to respond to those, and we'll get those answers out to you early next week.